Alright, sweet. So let's go ahead and get started on our first question. If you have questions, go ahead and raise your hands. Alright, sweet. So, define autotroph, provide 3 examples. Where do autotrophs obtain their energy from? So, an autotroph is going to be an organism. I can't see. An organism that takes inorganic energy, like light or chemical and turns it into energy. Three examples of those could include like plants, right? Like grass or trees, right? But also underwater in undersea vents, you can have chemotrophs, which basically take heat energy and the chemical energy from underwater sea vents, right? And they turn that into energy. So grass and trees, right? These guys take in light energy. And what is that process called when they take in light energy and turn it into sugar? Photosynthesis, that's right. Mr. Rodriguez. Yes, right. Skin services. Perfect. Okay, cool. You said. Alright. Sweet. So plants, green or trees, taking light energy. The other things include chemotrophs, right? So chemotrophs. And I'm not going to test you guys on chemotrophs, so don't like freak out. Chemotrophs are going to include like underwater organisms. Underwater. Okay, cool. So those are some examples too. Heterotroph. An organism that cannot produce its own energy. Must consume another organism to satisfy energy demand, right? So we all need energy. We need energy, right? But we can't go out into the sun and photosynthesize. So what we do is we get our energy from other organisms that either have it in themselves, so we can eat, you know, like a chicken. A chicken can't photosynthesize, but it has energy in it. Or we could eat something that does create its own energy, like a plant. So, long story short, they cannot produce their own energy. They have to consume it from something else that has energy. And those are going to include humans, right? I.e. humans, cows, fishes, that's good. Cool. And those are 3 just very basic examples. Okay, cool. Explain the difference between a chemical reaction and a change of state. Right, so this one we didn't really talk a lot about, so this is more to introduce you to an idea. The difference is, right here when we have CO2, right, and this is just an example. When we have CO2 being added into H2O, that is being turned into something completely different. the beginning and the end are two different things. But let's say we had water, right? So we had water, which is H2O, and then we turned it into a gas, and then we added heat, right? And that turned it into like, or let's see, if we had a liquid, right? Let's say we had a liquid, and then we added heat, then it would turn H2O into a gas, right? Right here, a chemical change is one where the reactants and products have different chemical compositions. Composition meaning like, CO2, H2O is not the same as H2 and CO3. With a state change, right? A state change meaning, gas, liquid, or solid. Right here, if we look at H2O versus H2O, the chemical composition is the same. It's not different. And because of that, it's a state change, meaning it's flowing between a gas, a liquid, or a solid. It's not a chemical change. So if you were to be asked the question, is evaporation a chemical change or a state change? Who can give me, a quick answer on what they think it would be? Daniel?
State change?
It'd be a state change, and why is that?
Because the form is still H2O, the formula is still the same.
Perfect. It doesn't matter if we're going from ice to a gas, anything like that. But if you're changing the chemical composition, right, where if we even were taking like calcium carbonate, and we're getting that from calcium and then bicarbonate, those two things, the beginning is not the same as the end. Cool. All right, so we just wanted to introduce that. Cool. All right, 4. How is energy stored? What is the name of this compound? What determines a high energy compound compared to a low energy compound? And we had a journal on that one day, so I'm going to make some space for the latter part. But how is energy stored? What is energy stored in? And I'll take the hand. Yes?
ADP?
ATP, that's right. So so the name of the compound that it's stored in, right, can be stored in ATP, it could be in glucose, right? So those are things that we often think store energy. But the other thing, right, so what releases this energy? What do we have to do in order to release this energy? What does ATP need to become? What happens to ATP when it releases energy? I'll take a hand. We went over this, we thought about repulsion, right? Something needs to happen. Remember when we're holding hands and I come over and I chop the hands and the hands splits apart. It splits apart. So what do you have to break in order for energy to be released? That's right. Both of you were correct. Bonds. Cool. So right here for 4, how is energy stored? Energy is stored in bonds. When bonds break, energy is released. Okay, cool. So the next one for 4. What determines a high energy compound compared to a low energy compound? Anybody kind of have an idea on this? This one was tricky, right? So basically what this one comes down to is the amount of repulsion you have between 2 items. So the first thing you have to do is, right, you're going to look at the bond. We're going to name this high energy versus low energy. So we look at the bond and we see, where it is. So, and then 2, what we're going to do is look at the repulsion between the 2 items bonded together. And repulsion, let's see. And what are the things that contribute to repulsion, right? What are those items? So charge, right? So if you have a whole bunch of alike charges next to each other, they're going to repel each other. So greater repulsion the higher the energy. When the bond is broken. And what are the factors that contribute into that? They're going to include charge, between alike charge. Sorry, a little bit verbose, but if you have a whole bunch of negatives next to each other, they're going to repel against each other. If you have a whole bunch of positives next to each other, they're going to repel. So, negatives versus negatives, positives versus positives. Right, so when we look at something like ATP, what we'll see, we go over here, is the 3 phosphates up top. What they're going to have is they're going to have oxygen, phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen, phosphorus. So 3 right here. Okay, cool. So when you see all these, right, all of these oxygens, they all have negative charges. And because they all have negative charges, there's a lot of repulsion going on between these. So when you break this bond right here, right, it's going to need a lot of energy. Perfect. All right, let's go ahead and move on to number 5. And I'll let you guys take note of that really quick. Sweet. And don't worry, if you didn't get it down, remember we're going to post this video. So everything is on the video. Cool. All right, so give yourself room to keep up. Hopefully you have the study guide done so we can look at it. You can correct it. So 5, is going to be explain the process through which energy is released. So energy is released, thank you, when bonds are broken. Imagine holding hand demo. Lean back, right? Great. Hand connection. Energy release. Perfect. All right, 6. This energy is driven by what force? Think about, so for 6, it's just going to be part of the same thing, right? So bonds are broken. This is driven by repulsion. All right, sweet. 7. In what processes of photosynthesis is light absorbed, is glucose released, right? So if we're going to draw out our chloroplast, right, which is going to be this guy right here, right? So I'm going to go ahead and draw that out. So in the first reaction, we have light coming in. And then we have water coming in. And then, what is the name of that reaction? I'll take a hand. It is a light dependent reaction. Light dependent reaction. Perfect, good job. You guys are all doing great. Okay. And then the thing that comes out of that is going to be, remember this is in plants, right? So what is going to come out of that light dependent process? O2, that's right. Okay, cool. And when we take in that energy, we're taking in light, and what we're doing is we're creating high energy compounds, including ATP and NADPH. You just need to know that those are a thing, right? And then they're going to go over to the light independent reaction. And you know that because no light is coming in, right? And in that light independent reaction, you have CO2 coming in, and those carbons are all combined together, and what they're forming in the end is glucose, which is C6H12O6. So you can see right here, there's a whole bunch of carbons. The carbons are coming from the CO2 to make sugar. And just to reiterate, right, this is called glucose. Sweet. And the things that are coming over back are including ADP and NADP+, right? Cool. That's coming back right there. Sweet. We're going to go over it. So in what processes of photosynthesis is light absorbed? Light is absorbed in the light-dependent reactions. Is glucose released? Glucose is released in the light-independent reaction. Is CO2 absorbed? That's in the light-independent reaction. Is O2 released? That's in the light-dependent reaction. So the reason why doing well on your quiz is going to help you here is if I ask you any of those questions, you can just write out, your model, and based on that, you should know, like, oh, that's the part where that happens, right? So if you're able to draw this, you can answer all those questions and any other question that comes up for photosynthesis. For instance, this. What is the chemical equation for photosynthesis? That is going to be 6H2O plus 6 CO2 plus light. And that is going to give you C6H12O6 plus, so this, right? 6, so 18. That's going to give you some O2, right? I think that's going to give you 6O2, actually. Yeah, 6O2. Cool. All right, 9. So, we can look at this and say, like, okay, glucose is coming out, right? So we know glucose is coming out. That's going to be part of our products. O2 is coming out. That's going to be part of our products. What things are going in? The things that are going in include H2O, CO2, and light. And we put that on the left side of the reaction. Those things are used to create the things coming out. So it's a nice little way to break it all down. What are the products of the light-dependent reaction? I'm just going to label this 9, right? So this is going to be 9. What are the products of the light-independent reactions? Okay, I misinterpreted that. So for the light-dependent reactions, we know that O2 is coming out, right? So right here, the answer to 9 is O2. And for 10, what are the products of the light-independent reactions? We know that that's glucose. So we're going to put that right there. Perfect. All right. So this one's a little bit more tricky. A mutation in a plant destroys chlorophyll B. This prevents the production of blank and blank, and this leads to the accumulation of blank and blank and blank. Right? So what in the world is Mr. Rodriguez getting at? So, what I'm getting at, right, is if you look at 7, if you take out light, right, let's just say, light was no longer a part of the equation. We just took it out. So right here you can see this, and we took out light, right? If you take out light, you cannot create O2, you can't create ATP, and you can't create NADPH, right? That makes sense. We don't have any light. But at the same time, for other reactions that happened previously, you still have these things being used up that already existed. So the light-independent reaction is still producing ADP and NAD+. So if I was going to ask you, if you took out light and you no longer had light, what things would be accumulating? Well, basically, the remainder of these things that were already existing, right, these are going to get used up, and then these things are going to come out, right? And those are going to accumulate. Let's say, does that make sense? Should I draw an analogy?
Yes.
Okay, so an analogy that could help, right, would include, let's say we were...
Does it recycle itself? Is that what you're saying?
Yeah, it recycles itself. So let's say, oh, I got it. Okay, cool. So let's say you're at your kitchen, right? And you know that when dinner happens, right, the flow between things is going to be dinner, where you get to eat, and doing dishes, right? So right here, whenever you have dishes being done, dishes cleaned, right? When you have dishes being cleaned, you have dishes coming over, and those allow you to eat dinner. And the same thing, when you eat dinner, you have dishes dirty. So dishes clean, clean dishes come over, right? And you eat dinner, and then dishes get dirty. Let's say, for instance, right, the thing that was coming in for dishes cleaned was soap. And over here, food was coming in, right? Cool. All right, so let's say you took out the soap. You still have all the clean dishes that were inside your cabinet. So you're still able to eat dinner because food is still coming in, right? So when you take out the soap, basically, you're able to use the remaining clean dishes you have. You're able to eat dinner. And the thing that you find accumulating because you cannot wash dishes are the dirty dishes. So you'd see a buildup, right? If you took out soap, if you removed soap, buildup of dirty dishes. In the same vein, when we look up here at 7, if you take out light, the thing that you're going to get accumulating, you're going to keep using the ATP and NADPH that you already have, but you're going to accumulate it because you cannot regenerate it. So what you would expect is if you take out light, you'd expect the accumulation of ADP and NADP+. Does that make sense? A little bit better at least? Okay, cool. If you have questions about that, please ask. So that was up to 11. Let's keep on trekking. Let's check our time too. Ooh. We are running low on time. Okay, let's keep going. All right, so,
Wait, so how do we fill that in? Yeah, actually.
Yeah,
like
it's
how
like
we
a fill
fill
in.
it
It's like, what would
into
be
the
the word?
yes. So, right here, for 11, right, this prevents the production of ATP and NADPH. And this leads to the accumulation of NADP plus, and then also ADP. short while glucose. Cool. All right, let's go on to 13. 13, the energy of the sun is harnessed in light-dependent reactions.
Wait, what's wrong?
Thank you. Okay, cool. What is the name of the plant organ that absorbs light for photosynthesis? That light organ is going to be called a chloroplast. 13, the energy of the sun is harnessed in light-dependent reactions. To drive the joining of let's see, to drive the joining of I think for that one I was meaning to say ATP and then NADPH. That's what I was getting at. So for these right here for ATP you have to be able to add together the phosphate for. So right here, you know you have 3 phosphates, right? And this is the rest of ATP over here. And then, you know, we're going to add these. So, when you have ADP, what you actually have is you only have 2 phosphates, right? So we're going to go ahead and take this one away. So what you need to be able to add to it is you need to be able to add another phosphate group. But remember, these things are both negative and alike charges repel. So basically what you do is you add light energy in and you use that energy to squeeze them together close enough to where you can form ATP. Which is going to include the 3 phosphates, right? So 3 phosphates, this is just another way of writing it out. It's the same thing, and these are going to be next to each other. Cool. Let's see. 14, write the reactants and products and chemical equations for light-dependent reactions, light-independent reactions, glycolysis, Krebs cycle, all those guys right there. Okay, so I'm just going to run through all of them very quickly so you can check your answers, right? Because that'll be helpful. So, it's getting a little bit noisy too, so let's go ahead and bring it down a little bit. Cool. Alright, so light-dependent reactions. I'm just going to list them in order. Light-dependent reactions are going to include light plus H2O coming together to form O2 plus ATP plus NADPH, right? And yeah, those are the things that come out. For the light-independent reactions, what you're using is ATP plus NADPH, and then you're adding CO2, right? And that is coming together to form glucose. These are simplified. If we wanted to write out the full things, we'd have to tell, I'd have to include over here like plus ADP plus NADP plus. But I'm going to abbreviate it. I'm going to leave out the extra stuff just so you can get the main ideas. So just know that. Okay, so don't worry about stuff like this. Okay, next one, glycolysis. Glycolysis is going to include glucose